Welcome back to our discussion of chance errors in sampling. In today's review exercises, we'll look at some problems that help us apply the concepts and calculations we learned in Chapter 20 to a variety of problems. There we go. First up, we have a problem here that's related to a coin tossing game. And you can see that we need to complete this table. So you can see in the table we have some columns related to the number of tosses, the number of heads and its expected value in the standard error, and the percent of heads expected value in standard error. And when we look at 100 tosses, we know that our expected value is for the number of heads is 50, and our standard error is 5. How did we find those? Well, the expected value is the average of the box. The box here, well, what is the box? You tell me. What's our box model look like for this coin tossing game? What numbers should I put in the box? Remember that the box is the population. And in this case, the population is the values of the coin. So we have heads and tails. And we can call heads ones because we are counting the number of heads. And we'll call tails 0. So this is your basic 1, 0 box. We haven't been told specific numbers for larger so yes, in each toss, we have a 50% chance of getting a 1 or a 0. But let's first look at how we can get so we have our expected value of 50 heads. I don't have space here. And 50 tails. And that's easy to see when we just have 100 tosses. Our expected value is the mean of the box times the number of draws. The mean of the box is 0.5. And the number of tosses is 100. So 0.5 times 100 gives us an expected value of 50. The standard error is the square root. I hate it when it does that. That's not divided, 100 divided by, this is the 100 tosses section. I recommend that when you are doing your own problems, you similarly label sections. Like if you start doing calculations for something, make sure that you clearly labeled what you're working on, because it's important to keep track of your terms, especially with the material we're doing now and in our next unit. So for 100 tosses, remember our expected value is equal to the mean of the box times the number of draws and the standard error is just the square root of the number of tosses times the standard deviation. The standard deviation here is going to be 0.5. How do I already know that? Because this is just a a minute. But if we want to look at the standard deviation for this box, remember we can use our shortcut here. So it's big minus small times the square root of the big fraction times the small. One minus 0 is always 1 times the square root of now 0.5 times 0.5. So this is 0.5. So see how we're able to find the standard deviation of a simple box like this pretty easily, much more quickly than more complex box. So square root of 100 times our standard deviation, which is 0.5. So our standard error is 5. See how we got those? Now we can apply the same idea to looking at 2,500. In this case, our expected value is, well, it's always equal to the mean of the box times the n of the draws. Now, though, it's 0.5 times the number of draws is 2,500. So our expected value is 1,250. And our standard error, remember the box is still going to have the same standard deviation. The standard deviation is not specific to 100 draws. This is just the standard deviation for this box. So our standard error is the square root of the number of draws times the standard deviation, or the square root of 2,500, times 0.5. This works out to 25 if you do the math. And in terms of the percent of heads, we think through this logically. Our expected value, remember, is always going to be equal to 50%, because that's the mean of the box and the percent of heads. It's the standard error as a percentage that changes. So the standard error as a percentage of heads is smaller as the number of tosses goes up. So let's just look at this one more time, because this process is important to feel very comfortable with. So when we have 10,000, our expected value is still the same formula, of course, but now it's equal to 0.5 times 10,000, or 5,000. Our standard error, you can just get by taking the square root of 10,000 times our standard deviation of 0.5. We'll see that it's 50. So note that even though the size of the standard error goes up, the standard error as a percentage of the number of heads gets smaller. So now it's half of 1%, or I just don't have space here. A moment. It was 0.5%. And if we did 1 million tosses, I'm sure you can see that the math would work out so that the expected value would be 500,000 with a standard error of 500. But the percentage of heads expected stays steady at 50%. But our standard error gets even smaller, so that now it's 0.05 of 1%. Or oops. So technically, let me rewrite these. Oh. So this is half of 1%, which is easy to consider, just half of the 1%. But the reason I'm writing it in this format is because when you get up to 1,000,000, it's a very small number. It's easiest to think about it as 0.05 of still 1%. So it's an extremely small proportion of 1%. Does that make sense? How we can see that as the number of heads increases, the raw size of the standard error increases, but the standard error as a percentage of heads decreases. A group of 50,000 tax forms has an average gross income of $37,000 with a standard deviation of $20,000. Furthermore, 20% of the forms have a gross income over $50,000. A group of 900 forms is chosen at random for audit. To estimate the chance that between 19% and 21% of the forms chosen for audit have gross incomes over $50,000, a box model is needed. Let's consider these questions, and how about you try to make some guesses at the answers. So first, let's consider A. Should the number of the tickets in the box be 900 or 50,000? I'm getting you every time on this, Molly. It's 50,000. It's got to be 50,000 because the box is the whole population. It's okay. I knew this is tricky. That's why I did so many questions that help us visualize this. The number of tickets in the box is the population. And we know that the population is a group of 50,000 tax forms. From that group of 50,000 tax forms, a group of 900 forms is chosen at random. 900 forms is our sample. So this is our population for the box, and our 900 forms chosen at random are the sample. One thing that tells us what the sample size is, or that one thing that gives us a clue to how that can help us when reading, discriminate between these two, is that we're told that the 900 forms are chosen at random. A sample is a group randomly chosen from the population, or ideally randomly chosen. However, a population can't be randomly, well, once established, a population is not randomly selected. Even though, as we saw in the one example, we could have a cross-sectional survey that employs random selection and then use that as a population for another study. But once it becomes a population, it's got parameters. And the random selection always applies to the sample. Okay, let's look at the next item, B. Each ticket in the box shows a 0 or a 1 or a gross income. Well, to think through this, we need to see, remember that we're estimating that we're looking at the chance of forms with the gross incomes over 50,000. So we can classify the incomes as over 50,000 or not over 50,000. So our box is zeros and ones. Now, true or false, the standard deviation of the box is $20,000. That's right. This is false. What is the standard deviation of the box? Well, it's equal to the square root of 0.2 times 0.8. Thus, it's 0.4. How did we know that? Because remember, 20% of the forms have a gross income over 50%. Our box is 0 and ones. Where the ones are over $50,000 and our zeros are under. And we know that the proportionately 20% of the forms are over, which means that 80% are under. And as proportions, these are equal to 0.2 and 0.8. Remember, we use our proportions. We have to use the proportions in the standard, in the calculation, and then convert to a percent. So now let's look at D. True or false, the number of draws is 900. True. The draws are the sample. And our last item, find the chance approximately that between 19% and 21% of the forms chosen for audit have gross incomes over 50%. So the number of sample forms with gross incomes over 50,000 is like the sum of 900 draws from the box. Here we have an expected value for the sum equal to 180. And the standard error for the sum, well, let's consolidate our standard deviation here. Thus, the standard error for the sum is the square root of number of draws times the SD. Thus, it's square root of 900 times our standard deviation of 0.4. So the standard error is 12. Thus, the number of sample forms with gross incomes over $50,000 will be around 180, give or take 12 forms. Now, 12 out of 900 is about 1.3%. Whoa, what happened there? Thus, the percentage of forms in the sample with gross incomes over $50,000 is 20%. The percentage of forms with a gross income over 50,000 is 20%, give or take. Oops. Give or take 1.3%. If we look at this on a normal distribution, it's mostly normal distribution, let's assume it's actually normal. You can see that 20% is our expected value. We're looking at the range that's 21%, down to 19%. We need this area. And if we convert these points to standard scores, we can get this percentage. So to get our standard units, remember we are looking for our observed or projected minus expected over the standard error. Now we're using our percentages. So for 19, the z of 19% is going to be 19 minus 20% divided by our standard error of 1.3. And you see this works out to 0.7, there we go, 0.77 approximately. If we go to the other side and we look at our standard, our z-score for 21%, we can see that it's going to be, this is a negative, sorry, 19 minus 20 is negative. It's just going to be the flip side of this, or 21 minus 20 over 1.3. So now we end up with a positive 0.77. We can put these on our standard unit line here that doesn't have enough space, but the standard score would be 0.77. Our lower unit standard score is negative 0.77. And so this fraction is approximately 55%. You can look it up exactly in your z table, but we just look up these z scores and you'll see that's a rough approximation. So the chance is approximately 55%. And I realized that I left off the very last portion of this. Let's see if this will work now. We clearly don't have space to do much here. Let's see. Sorry, I don't know if you can hear, but my computer is feeling especially overworked at the moment. So let's do this final item. I do like this problem, and you will probably see one like this on the exam. I think this is a fantastic problem, and I echo your sentiments. Let's finish this last one, F. with the information given, can you find the chance, approximately, that between 9% and 11% of the forms chosen for audit have gross incomes over 75%? What do you think? Can we find it? Well, the first thing to ask yourself is, do we have any information that tells us the proportion of forms that have gross incomes over $75,000? Nope. We don't have that, so we can't do this part. F is not possible to do because we need to know the percentage of incomes over $75,000 in our population or in the box. This is not one standard deviation. So it's tempting because a lot of times we use problems where they work out so that the range is one standard deviation, but this is 1% difference from the expected value, not one standard deviation. The standard deviation, it's actually 0.77 standard deviations from the mean. How do we know that? Because when we found the standard scores down here, which we'll rewrite one of them just for clarity's sake, we have in the numerator a 1, but in the denominator we have 1.3. So this is 1 out of 1.3, or 0.77. Yes, we frequently do use the one standard unit, but it's not a guarantee. Okay, yeah, this is a great problem. Look at how this problem illustrates lots of topics that we've discussed across this whole unit. You've got to make a decision about what's in the box, what's on the tickets, the standard deviation and the sample, and you apply the normal curve. So this is a great problem, and I think it's a very nice example. Also, it had an example of a time when we don't have enough information, which is another option you frequently see on your exams. So I would advise that you make sure to feel really comfortable with doing a problem like item 3. Now let's look at item 5. On average, hotel guests who take elevators weigh about 150 pounds with a standard deviation of about 35 pounds. Okay, an engineer is designing a large elevator for a convention hotel to lift 50 such people. If she designs it to lift 4 tons, the chance it will be overloaded by a random group of 50 people is about blank. So let's figure out how to find that. The total weight of the group is like the sum of 50 draws from a box. The average of the box is 150 pounds with a standard deviation of 35 pounds. we go. Okay. Thus, the expected value for the sum and the standard error for the sum are items that we need to find in order to answer this question. Remember that our expected value is equal to the mean of the box times the number of draws. In this case, our expected value works out so that the mean of the box, remember, is 150, and the number of draws is 50 people. So the expected value is 7,500. And then the standard error for our sum is the square root of our number of draws times our standard deviation, or the square root of 50, times 35. Thus, it's approximately 250 pounds. So we're almost there to our answer. We need now to know the chance it will be overloaded by a random group of 50 people. Well, we already have the values for our group of 50 people, and now we can, to get this probability, we can use the normal curve to get the probability of any particular score. So in this case, we need to remember that the overloaded is equal to 4 tons, which is equal to 8,000 pounds, because we need to keep our units, our figures, in the same units, right? Thus, to get to apply the normal curve here, we know that we have 7,500 as an expected value. 8,000 pounds is the observation we're interested in, and we can get the standard units for this. So we already know the standard units for the expected value are 0, and to get the standard units for 8,000, they're equal to that observation minus the expected value divided by the standard error. Thus, this is A equal to 2. So this score is 2 standard units from the mean. And now we are ready to answer our question. We want to know the chance it will be overloaded. Well, if it's overloaded, that means that the weight is above 800 pounds. So we want to know the chance of a random sample of 50 people falling in this proportion of the curve that's 2 standard units above the mean or higher. This proportion is equal to approximately 2%. So it's, let me write it as technically 2.5%. But so there's a 2.5% chance of overloading the elevator, which, although small, is still highly problematic because we're talking about overloading an elevator. 50 people could die if it gets overloaded. So probably a better elevator is needed in this case. No, this is a good problem because we have to walk through the steps of getting our expected value and standard error and apply it to the normal distribution. Problems that apply things to the normal distribution will be pretty popular on this exam and the final exam. When you think about it, we've had normal distribution problems in every section of every unit of our course. Now we have a problem with 500 draws made at random from this box with 60,000 zeros and 20,000 ones. Let's think through these options. Out there in the peanut gallery, please make your voice heard and vote on these as we go through them. So let's look at A. These are all true or false. The expected value for the percentage of ones among the draws is exactly 25%. This is true, very good. How can we find this? Well, we know that there's 80,000. That's the population, and there's 80,000 total in it. The ones are 1/4 of that. 20,000 out of 80,000 will end up to be 25%. Next, the expected value for the percentage of ones among the draws is around 25%, give or take 2% or so. What do you think? Is this true or false? This is false. Very good. It's false because the expected value is computed with no chance error. It's just the expected value. The chance error is a separate thing. So the expected value equals the percentage of ones in the box, as in item A. Now item C, the percentage of ones among the draws will be around 25%, give or take 2% or so. Well, this one is true again. It's true the percentage of ones among the box will be around 25%, give or take 2% or so, because now we're looking at the percentage of ones among the draws, among the 500 draws. And we're not asked about the expected value, but we're just asked, is this true? Well, sure, it's true. The percentage would be around 25%. That's our expected value, give or take a standard error of 2%. Will the percentage of ones among the draws be exactly 25%? For part D, what do we think? This is going to be false because we can't know whether the exact percentage of the number of ones among the draws until the draws have been done. This is just 25% is just our expected value. The percentage of draws will be, the percentage of ones among the draws will always be off the expected value due to chance error. And in this case, our standard error is about 2%. So now let's look at E. The percentage of ones in the box is exactly 25%. What do we think about item E? In this case, it's true. The percentage of ones in the box is exactly 25%. Here, this item is just asking us about the percentage of ones in the box. We already know that the percentage of ones in the box is 25%. One last item, the percentage of ones in the box is around 25%, give or take 2% or so. Is that true or false? Remember that Albert Einstein said, or Linus Pauling actually is the one who said, is the way to come up with great ideas is to have a lot of ideas and throw the bad ones away. So yeah, this is false. Very good. Why is it false? Well, we already know that if the percentage of ones in the box is exactly 25%, it's exactly 25%, not around 25%, give or take a standard error. The box is static. The box doesn't change. It's the draws from the box that have a standard error in them. Thus, we know what's in the box, so there's not any need for any error term. This is another great item. Look at how this has some nice true-false questions that give us some good applications of these concepts. I like this item. Wink, wink. Now let's, yeah, I'm really subtle. Now let's look at one more item. Actually, two more. So let's see our next one. 600 draws will be made at random with replacement from the box 001. The number of draws, the number of ones among the draws will be around blank, give or take blank or so. Well, we can fill these in. First, let's fill them in conceptually. The number of ones among the draws will be around the expected value, right? Give or take a standard error or so. And so to get the numbers that go in here, we just need to get the expected value and standard error for this box. The number of ones is the sum of the draws. So the expected value for the sum, as always, is equal to the mean of the box times the number of draws What's the mean of this box? %. Yep. It's actually 0.3 because we're going to keep it in our proportionate form for now, times the number of draws, 600. Thus, the expected value for the sum of 600 draws from this box is 200. And we can get our standard error by looking at the square root of the number of draws times the standard deviation Once again, we need to get our standard deviation, but we still have a box that's big, small. So we've got big minus small divided by the square root of the fraction that's big and the times the fraction that's small. Big minus small, 1 minus 0 times the square root of, we know the fraction that's big is 0.33. Or 1/3. You could do this easier or more accurately because it's a repeating fraction. And when we work through this standard deviation, what do we get? Okay, so we get a standard deviation here of 0.46, let's say 0.47. Our number of draws is 600. And we end up with a standard error of about 12. So we can fill in the blanks here we know that the number of ones among the draws will be around 200, give or take 12 or so. Okay. So another great problem. Boy, this chapter is filled with really great problems. Isn't it nice how this chapter really builds on the other subjects in this unit so that it gives us a lot of great problems to look at. And we'll look at one more today. In this one, we have a university has 25,000 students, of whom 17,000 are undergraduates. The housing office takes a simple random sample of 500 students. 357 out of 500 are undergraduates. Let's fill in the blanks. For the number of undergraduates in the sample, the observed value is blank, but the expected value is something else. Well, first we need to think about what is the box model here. I'm pretty sneaky. So 357 is our observed value, or did I say that? 357. We already know that. They took a random sample, 500 students, and 357 were undergraduates. As a percentage, 357 is 71.4%. But if we want to get our expected values, we need to make a box model here. And we'll assume that we've got a 0, 1 box where ones are undergraduates and the zeros are not undergraduates. Let's assume they're graduate students, although there are other categories, but let's just go with this. How many tickets are in this box? How many total is this equal to? Yes! Yes, it's 25,000 because this is our population. Very good. And we already know the proportions of the tickets in this box. We'll do that. Here, there's 17,000 are undergraduates, and the rest are not undergraduates, or 8,000. Okay, and we can now get our expected value. If we get first of mean for this box, so let's think about what are the knowns and unknowns we're going to need here. First, we need to know the mean of the box to get the expected value. And we're going to want to get ultimately the expected value for the box too. Let's start with the mean. To get the mean of this box, we're just summing the ones and zeros here. We already know there's 17,000 ones. Out of a total of 25,000 possible participants. So the mean for the box is equal to the fractional representation of the ones, or 0.68. Our expected value is equal to the mean for the box times the number of draws. How many draws did we do? 500. So the mean of the box is 0.68. Our draws are 500. So the expected value for the box is 340. So that completes part A. The observed value was 357, but the expected value was 340. In terms of percentages, the observed value was 71.4%, but we already know the expected value percentage is going to be 68%. It's just the flip side of this fraction. We could prove it by taking, if you want to prove it, you can take your 340 out of the total n, and it just works out back to 0.68, the mean of the box. As a percentage now, it's 68%. Excellent job, everybody. These are some really great items. I encourage you to practice the other exercises in this chapter. So even though we were only assigned the odd numbers, remember the even numbers are also excellent problems with good representations of these concepts as well. Usually a lot of them are alternate versions of the other problems. So take a good look when you're working through this chapter. It's a great one to help you review for the exam. While you're doing that, remember, learn from yesterday, live for today, and hope for tomorrow. The important thing is to not stop questioning. Don't regret guesses you made that were wrong. That it's good to make the mistakes and then learn from them. Learn from yesterday, learn from your last mistake, and build on that to go forward. Keep asking questions like, how can I learn from yesterday? And if you want guidance and help when you're thinking through how to apply this idea to your statistics studying, feel free to reach out to me and I'll help. The important thing is not to stop questioning. Questioning yourself, you can question me too. As we all know, for the most effective way, do some statistics every day.